I'll talk about what is probably the most basic and fundamental case of applying group representation theory to physics. And generally speaking, it is not complicated at all. I tried to make this video as clear as possible for physicists. And what representation is, you can find out in another video. The link in the description. Physics is full of symmetric objects, atoms, optical and acoustic resonators, molecules, and even space itself. There is almost always some symmetry. Take, for example, molecular symmetry groups. Can we, just by knowing the symmetry, say something about the system, like the eigenmodes of a resonator or the solutions of the Schrödinger equation? It turns out we can. And we can say it without doing calculations or solving any equations. We can immediately impose many constraints, for instance, on how such a resonator scatters, on selection rules, or on how a molecule vibrates. Even the structure of energy levels in an atom is a direct consequence of symmetry. And more advanced topics in theoretical physics, Lorentz transformations, elementary particles, are nothing but pure representation theory. But in this video, I'll stick to very simple cases. So let's take an eigenvalue problem. Quantum mechanics, optics, acoustics, doesn't matter. We won't worry about whether it can be solved analytically, about normalization of solutions, and so on. Suppose we are looking for the eigenmodes of a resonator. What can we say about these modes if we know only the symmetry of the resonator? It turns out quite a lot. First, what does it mean that a resonator is symmetric? It means that under certain symmetry operations, such as rotations or reflections, it remains the same. Like this triangle under rotation by 120 degrees, rotation by 240 degrees, and reflection in 3 planes. Such operations form a symmetry group. Point groups and examples of symmetries are shown in this picture. And a symmetry group has irreducible representations, just like any other group. In fact, it's easy to look up which representations belong to which group. This has been known in mathematics for a long time. What representation is, you can also learn from the previous video. Let's consider a simple example. Take the group D3H. This could correspond to a resonator shaped like a prism with an equilateral triangle at its base. Such a group has 6 representations called A1', A2', A', and the same with double primes. You might ask, so what? Well, a long time ago, Wigner said the following. If an eigenvalue problem is invariant under the transformations of a group, then its eigenfunctions or its eigenmodes transform according to the irreducible representations of that group. In the case of the triangular prism, this means there are only 6 possible ways the modes of this system can behave. 6 distinct types of eigenmodes. In reality, there is infinite amount of eigenmodes, but they fall into just 6 categories. And Wigner also said that the degree of degeneracy is equal to the dimension of the irreducible representation. A short side note. If you're still watching, that means this video is at least a bit useful for you. YouTube hates me and barely recommends my videos, so if you're still here, please like and subscribe. That's my only motivation to keep making this. And a huge thanks to everyone who strongly supported my previous video. So, what does this give us? First, we can label the modes with these letters. For example, this eigenmode we call A1'. It is the best naming, I swear. Of course, we usually have infinitely many modes that transform according to this representation, but we can number them in order of increasing frequency, for example. The label A1' will already tell us everything about the symmetry behavior of that mode. How do we know which representation to assign to a mode? Mathematics gives us character tables. A character is just the trace of the representation matrix. Let's try to classify a mode like the one in the picture, where red and blue show different signs of the pressure function, say in acoustics. Look at reflection in the horizontal plane. The mode is clearly odd, so the character is -1. Now look at reflection in the vertical plane. Here it is even. So the mode transforms according to A2''. If we check the remaining symmetry operations, everything matches. Now let's take another mode. This one is odd under both reflections. That means it transforms according to A1''. By the way, this great slide was made not by me but by my students. Many thanks to them. That's how we produce the whole classification. Moreover, thanks to irreducible representations and Wigner, we know which modes are degenerate and which are not. And we know the degree of degeneracy. For example, in a triangular prism, we can have doubly degenerate modes, but never triply degenerate ones, aside from rare accidental degeneracies. In a cube, however, triple degeneracies do occur. How can we understand what such modes look like in general? In resonators, eigenmodes are often expanded in a multiple basis. Multiples are convenient, intuitive, and form a nice basis. But what do we actually mean by multiples? That's just slang. In scalar problems like acoustics with boundary conditions, I mean scalar spherical functions. In vector problems like optics, I mean vector spherical harmonics. They describe the angular part of the modes in spherical resonators. It turns out mathematicians have long known how spherical harmonics behave under all symmetry operations, and in particular, which irreducible representations of finite groups they transform according to. For example, you can use this fun table. Link in the description. Just keep in mind that such tables often have small inaccuracies, though nothing critical. This table here shows which spherical functions correspond to which irreducible representations. Group theory gives us the multipolar content of all types of eigenmodes instantly, not quantitatively but qualitatively. A mode that transforms as A2U can only be built from multiples that also transform as A2U and no others. The same holds for other representations. So we just open the table, check which multiples transform as A2U, and conclude. The mode is made of exactly those multiples, and we get the whole multipolar classification of the eigenmodes. That was for scalar problems and spherical functions. A detailed classification, explanations, examples, and consequences are discussed in our somewhat educational paper. What about optics and vector spherical harmonics? With them, it's simple. Check out another video on this topic where you can see that all electric multiples with given indices behave exactly like scalar spherical harmonics. They transform the same way under all rotations and reflections. Magnetic multiples, however, have the opposite parity under reflections, meaning they carry the opposite character of the representation under every possible reflection. This is easy to take into account, and it gives us probably the most informative classification of optical eigenmodes in resonators of any shape. So we also have the whole classification of the optical eigenmodes. This is extremely useful, for example, in scattering problems. If an incoming wave transforms according to some representation of the symmetry group of the resonator, it can only excite modes that transform according to that same representation. And if we excite the resonator with a single multiple by crafting the incoming wave in a clever way, scattering will still produce all other multiples contained in the same eigenmode. It also becomes clear what symmetry needs to be broken in order to make certain multiples. I'll probably cover that in more detail in future videos, along with a very powerful operator that helps explain how to build tables like the one with spherical functions when you have more complicated functions, not spherical. And yes, everything so far was only about the angular structure of eigenmodes, not the radial part. We also ignored what happens near the resonator boundaries, as well as convergence issues and so on. But symmetry doesn't care about any of that. We can just look at the far field.